In this section of chapter 13, I would like to discuss homework problems from the book. Now, a few expressions that you need to know before we apply them in solving problems. Like vapor pressure lowering is given by mole fraction of solute times vapor pressure of pure solvent. Mole fraction means total number of moles of solute divided by the total number of moles of solute plus solvent. So total number of moles at the bottom. Boiling point elevation is given by Kb, a constant, times molality. Melting point depression will be given by Kf, that's also a constant, times molality. In case you didn't remember what molality is, let me write down. Small m stands for molality, which is given by moles solute divided by kilogram of solvent. So that's how you get molality. So both boiling point elevation and melting point depression would involve molality of solute. Osmotic pressure, on the other hand, would need molarity. Molarity is expressed by capital M, and which is given by moles of the solute on the top and liter of solution on the bottom. So that's molarity. We will begin with problem number 33 from chapter 13. So 13.33 is coming from page 550, and this is from Brown LeMay Burston book of 12th edition. The question is, which of the following in each pair is likely to be more soluble in hexane? So they want you to find out which of the pair of substances will be more soluble in hexane. Now remember, we mentioned about like dissolves like. So let's write down that. Like dissolves like. There's a common saying in chemistry. That means nonpolar molecules would dissolve in nonpolar solute. Polar molecule would dissolve in polar solute. And hydrogen bonding solute. Again, hydrogen bonding is both polar as well as hydrogen bonding compound, like water. It has both polarity as well as ability to hydrogen bond. And they, again, would like to dissolve similar kind of substances. So let's go over this problem. First, we need to find out, since question is asking about solubility in hexane. This is hexane. 1, 2, 3, 4, 5, 6. 6 carbon, and rest are all hydrogens. You stick in hydrogen in such a way that each carbon has 4 bonds. So if I want to fill in, there'd be 3 hydrogens here, 2 hydrogens here, 2 hydrogens here, 2 hydrogens, 2 hydrogens. Always carbon, neutral carbon would have 4 bonds. So this is hexane. Now, if you have doubt about polarity, you can look at figure 8.7 that gives all electronegativity values. Now, electronegativity of carbon and hydrogen are pretty close. So carbon, let's write down some of these figures. Carbon is 2.5, hydrogen is 2.1. That's a very small difference to make a polar bond. So this makes it a nonpolar compound. So this is nonpolar. So if we're going to use it as a solvent, let's see which of the pair would be more soluble. Part A, carbon tetrachloride. So you're going to look at carbon tetrachloride. This is Cl, 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 Cl. That's carbon tetrachloride. And calcium chloride. Calcium chloride, calcium is from group 2A and Cl is from group 7. And these give ionic compounds, calcium 2 plus, Cl minus, and Cl minus. That's calcium chloride. Now what kind of compound carbon tetrachloride is? Let's look at each bond carefully. Each bond is a polar bond because Cl is a lot more electronegative than carbon. So this is the force, dipole force. The net effect of these three forces will be balanced by the fourth dipole moment going outward. Let me show you with red ink so that you know. So this red one towards Cl, the fourth Cl, is going to balance the other three dipole forces. In other words, this becomes a non-polar molecule. And calcium chloride is ionic. Now let's apply like dissolves like. Non-polar would go in non-polar solution solvent. So calcium carbon tetrachloride would be soluble in non-polar hexane. On the other hand, ionic calcium chloride will not be soluble in hexane. Let's see what we have in part B. Part B, benzene and glycerol. Again, same thing, just to save our space here. So let me just draw benzene so that you know what kind of structure benzene has. This is benzene. All carbon-carbon double bonds. And glycerol has lots of OH groups. Let me write down that in this manner. CH2OH, CHOH, and then CH2OH, CH2OH. Now OH, the hydrogen can give hydrogen bond. So this is hydrogen bonding compound. So let's write down hydrogen bonding compound. And benzene is non-polar. The solvent in which you are trying to dissolve is non-polar. So obviously benzene would be more soluble than hydrogen bonding compound glycerol. Now part C, for part C, you need to find out whether octanoic acid or acetic acid more soluble in hexane. Octanoic acid, from the name you know that octane has 8 carbon. 1, 2, 3, 4, 5, 6, 7, 8, COOH. That's octanoic acid. And acetic acid. I left out hydrogen. And you know how to fill in with hydrogen if you want to. Now in octanoic acid, of course, both have COOH group. So that's in common. So let me draw a line here to separate with the other questions. But octanoic has a large alkyl group. You can see here it's a pretty large alkyl group. Whereas in acetic acid, it's a small molecule, and you can see that there are only 2 carbon, but here a bulk part of that compound would be hydrophobic. And in case of acetic acid, only the methyl group, the first one, is hydrophobic, but that's such a small part of the compound, so it's really not going to influence much in dissolving in nonpolar solvent like hexane. On the other hand, in octanoic acid, since the major part is nonpolar segment and only this part, the small part, is the polar group. So octanoic acid would be more soluble. So let's write down that. More soluble. And acetic acid would be less soluble in hexane. Okay, hopefully you understood this. So in big molecules, you have to look at what kind of bonding you have, what functional groups you have. If you have a large alkyl group, and that part would be nonpolar, would not be attracted to water, but they'd be attracted to nonpolar solvent. And in this particular case, we have nonpolar hexane, and that's why overall molecule would show much greater solubility in hexane. Now we're going to do problem number 34b. Now here the question is about solubility in water as a solvent. So let me first write down those two. We're going to do part B only. And in 34b, we have propionic acid and sodium propionate. Which of the following would be more soluble in H2O? So let me write down the formula. Since it's propionic acid, 3 carbon. And the other one is sodium propionate. 1, 2, again without the hydrogen attached to carbons. This is O minus and sodium plus. So let's identify what kind of compound you have. This is ionic, and this one is polar. It can also give hydrogen bonding, but only thing is it has now these 2 carbon which are nonpolar or alkyl group. So it has a polar end, but an also nonpolar alkyl group. On the right hand side, you have ionic compound. Always ionic compound is highly soluble in water. Just like sodium chloride is highly soluble in water. So answer is the ionic compound is going to be more soluble in H2O than propionic acid. So always keep that in mind. If I have an ionic compound, that would be always more soluble in water. Now we're going to do 45b. In 45b, the question is calculate molality of the following solution. So asking for what is small m. Now small m stands for moles of solute. In this particular problem, they're giving 4.80 grams sodium chloride. So let me write down on the right side. 4.80 gram sodium chloride and 0.350 liter of water. 0.350 liter of H2O. So that's given. So let's put that on the side. So molality is given by moles of sodium chloride divided by, because sodium chloride is the solute, kilogram of solvent, kilogram of H2O. Now from gram I can easily calculate moles. So let's first show you the calculation of mole. 4.80 gram sodium chloride. I always think this way, MGP, mole gram periodic table, or gram mole periodic table. So since I want to go from gram to mole, I'll have to look at periodic table for masses. And this is what I have, times 1 mole sodium chloride divided by, you look for mass of sodium and mass of Cl. So mass of sodium is about 23, and each chlorine is 35.5. So that gives at the bottom 58.5, and this value is 0.0821. 0.0821. So that's the mole of sodium chloride. So I should write down here, this is mole NaCl. Now I need to know the kilogram of solvent. We have liter given, so let's change that to milliliter first. 0.350. Since they gave liter, let's multiply that by 10 cubed to get ml. And water density is 1, close to 1, 0.00 gram per ml. So that gives me gram, and then I'm going to divide by 1,000. I don't have any space here to get in kilogram. So first you get in gram, then divide by 1,000 to get kilogram. So this gives me 0.350. Okay, let me divide by 1,000, that we don't get confused. 0.350 kilogram, and these are the figures I need. So I'm going to need this figure. I also need this figure in order to get molality. So now molality will be given by moles of sodium chloride, which is 0.0821, 0.0821 divided by kilogram of water, which is 0.350. 0.350 kilogram H2O. And this gives 0.234. 0.234. So molality of sodium chloride in the solution is 0.234. We are now going to do problem number 71. So this is 13.71. The question is, list the following aqueous solutions in order of increasing boiling point. So they gave 0.120 molar glucose. So let me write down that. 0.120 molar glucose, 0.050 molar lithium bromide, and 0.050 molar zinc nitrate. Since we need to find out the order in which boiling point is going to increase, first we need to find out how many particles you can get in each case. Glucose doesn't break down. So if I have 0.120 molar glucose, it remains as 0.120. So 120 molar glucose. Lithium bromide breaks down into lithium plus and Br minus. So you're going to get 2 particles per lithium bromide. And each of these particles would have concentration of 0.050 molar. Think it this way. If one lithium bromide breaks down, you get one lithium plus and one Br minus. If 0.050 molal LiBr breaks down, you get 0.050 molal lithium plus and 0.050 molal Br minus. So altogether you'd have 2 times 0.050, and that gives you 0.10 molal particles. In case of zinc nitrate, again, zinc nitrate breaks down into 3 particles: zinc 2 plus, NO3 minus, and NO3 minus. So keep in mind, 1 zinc nitrate breaks down, you get 1 zinc and 2 NO3 minus. So 0.050 molal zinc nitrate breaks down, you get 0.050 molal zinc and 2 times that of nitrate. So altogether you're going to have is basically 3 times 0.050. 3 times 0.050, and that's going to give you 0.150 molal particles. Because these are colligative properties. It depends upon how many particles are there. So some of these would break down just like lithium bromide and zinc nitrate. Now let's identify the largest particle concentration, which is 0.150. Since it's the largest particle concentration, so boiling point would be largest. There would be largest increase in boiling point of water because you're adding these to water. So that's going to be largest. And the next largest would be 0.120. Basically go by these numbers. And the lowest one would be 0.10 molal. So let's now organize in increasing order as this question is asking for. So 0.050 molal lithium bromide less than 0.120 molal glucose less than 0.050 molal zinc nitrate. So you need to order them in terms of original substances. So that's the answer to this question. Let me now go over number 72. So 13.72. In this question, it's a similar problem, except here you deal with freezing point. They're saying that list the following aqueous solutions in order of decreasing freezing point. The first compound is 0.040 molal glycerin. 0.040 molal glycerin. That's an organic compound and it doesn't break down. It's primarily the ionic compounds that break down in water. And then we have 0.020 molal KBr. So 0.020 molal KBr and 0.030 molal phenol. Only KBr would break down into 2 particles per KBr. The others would remain intact in the solution. So basically, number of particles for the glycerin would be 0.040 molal But for the second one, it's going to be 2 times larger, 2 times 0.020. Make sure you understand that because KBr breaks down into K plus and Br minus. So this is going to be 0.040 molar ions. In case of phenol, it would be as it is because it doesn't break down, 0.030 molar concentration. Now, if you're wondering, how do I know whether a compound is going to break down? Try to find out whether it's an ionic compound or not. If it is an ionic compound, it's going to break down. If it is non-ionic compound, it would not break down. Okay, now look for the highest concentration of particles. That's 0.040. You have two numbers the same. So the value would be the same for glycerin and KBr, and phenol has 0.030. Now keep in mind, these are the solutes is going to depress freezing point from 0 degrees centigrade to a lower value. So the largest concentration would cause the largest decrease in freezing point. In other words, you get the smallest freezing point. If your freezing point of water is 0, say largest drop would be largest drop would mean the lowest freezing point that you're going to get for the solution. So based on this, and this time we are going to write down decreasing order of freezing point. 0.040 would give the smallest freezing point. So let me write down this. The smallest freezing point. Smallest freezing point. So the largest one would be for phenol. So I'm going to write down that freezing point order would be 0.030 molar phenol greater than 0.020 molar KBr, which is greater, that's equal to, I'm sorry, it's not, because those two numbers are same, 0.040, 0.040 equal to 0.040 molar glycerin. So make sure you ignore this. This is nothing. That's equal. So these two would give you the same concentration of particles in molality. Now we are going to do number 73D, chapter 13. So 73D. In this question, you are supposed to calculate freezing point and boiling point. So let's write down what they're asking for. Freezing point and boiling point. Of course, you have aqueous solution or water solution where you added 2.04 gram KBr. So 2.04 gram KBr and 4.82 gram glucose. 4.82 gram glucose is C6H12O6. In 188 gram of water. So they added this in 188 gram. So let's change it to kilogram because molality is defined in terms of number of moles per kilogram of solvent. So dividing by 1,000, you get 0.188 kilogram H2O. Now let's first calculate the moles. From gram of KBr, I can calculate moles of KBr. So you need to have, by looking at periodic table, you get gram mole relationships. So it'd be 39.1. Let's write down here. 39.1 plus 79.9 for Br. That gives, this is gram, That gives mole, kBr. And keep in mind, it's not just the mole of substance, it's also mole of particles. You have to take into account how many particles you get out of kBr. From each kBr, you get 2 particles. So you need to multiply that by 2 in order to get the fine number of particles. So this part gives number of kBr. Since each kBr splits into 2 ions, so you have to multiply that by 2. So the number that I get is, let's use a different color, is 0.0342. 0.0342 is the molar particles. Now, starting from glucose, 4.82 gram of glucose, let me calculate mole of glucose. Again, by looking at periodic table, I can write down the bottom you have 6 carbon, 12 times 6, that's 72. 12 hydrogen, that's mass would be 12. And then 6 oxygen, 96. Each oxygen 16. 96, that gives mole. So number of moles I'm going to get would be same as number of particles because glucose doesn't break down. So you're going to get 0.0268. Mole of particles. Now the total number of particles, total mole of particles equals to, those two numbers needs to be added, 0.0342 plus 0.0268. 0.0268, and that gives 0.061. So that's total moles of particles. And molality would be given by total moles of particles. So M would be defined as 0.061 divided by kilogram of solvent, which is 1.88, which is 0.188. And this gives 0.324. So I got molality of total number of particles available in water solution. Now I can calculate boiling point elevation as well as freezing point depression. So delta TB will be given by KB, that's constant, times the molality. And KB is known for water, which is 0.51. And already we know the molality, which is 0.324. And this gives me 0.165. That means boiling point has to be elevated by this quantity or increased by this quantity. And we know the normal boiling point. So boiling point of the solution, let's write down with a different color. So boiling point for solution after you mixed all these substances would be normal boiling point of water, which is 100 degree, plus the increase of boiling point by this quantity, 0.165. Remember, when you add a non-volatile solute, it increases boiling point by delta TB. So that needs to be added to the normal boiling temperature. So you basically get 100.165. 165 degrees centigrade. So that's the boiling temperature of the solution. Let's now calculate freezing point from depression of freezing point. So here we are going to use delta T, depression of freezing point, will be given by KFM. Again, KF is a constant, for water is 1.86. So 1.86 times the molality, which is 0.324, 0.324 equals to 0.603. Make sure you double check my calculation. So freezing point would be depressed by 0.603 degrees centigrade. Now let's get the freezing point now. Okay. The freezing point of the solution would be normal freezing point of pure water, which is 0, and that's depressed. Depressed means it went downward, so it's minus 0.603. And final temperature is going to be, freezing point is going to be 603 for the solution. That means when you add those solutes, the new freezing point is going to be minus 0.603 degrees centigrade, and the boiling temperature would be 100.165 degree centigrade. Now we're going to do number 75. So that's chapter 13, number 75. In this question, they're asking how many grams of ethylene glycol must be added. So how many grams? The question is asking for gram. For ethylene glycol, the formula is C2H6O2. O2 must be added to 1 kilogram of water. So 1 kilogram H2O. So how many grams of C2H6O2 must be added to 1 kilogram of water to produce a solution that freezes at minus 5 degrees centigrade? So the solution has freezing point of minus 5.00 degrees centigrade. Now question is, how do I start this problem? Now question is dealing with freezing point. So let's think about freezing point depression, because you're adding a solute into water. So freezing point has to go down. So let's calculate depression of freezing point, delta TF, which will be given by KFM. And we already know the constant KF for water is 1.86. So let's use that number. So it's going to be 1.86 times M. Now they gave you the freezing point, which is minus 5 degree. Now keep something in mind, that freezing point delta TF is the depression. Delta TF would be given by how much it was depressed. So normal freezing point is 0 degrees centigrade for pure water, and it's depressed by this quantity, so it'd be minus 5.00. So that gives me 5. Just by looking at this number, you'd know that it's depressed by 5 degree, because freezing temperature is 0 degree. So if it's depressed by 1 degree, it becomes minus 1. Depressed by 5 degrees, it becomes minus 5. So just simple observation will lead you to the same answer. So freezing point depression, or freezing point is depressed by 5 degree. Depressed means going downward. So make sure don't get confused between depression and elevation. Elevation means going upward. Okay, now we got this delta T is now 5. So let's plug in that number here. So 5.00 equals to 1.86 M, and I can calculate the molality, which is equals to 2.69. That's moles per kilogram H2O. Now keep in mind, this is the moles of solute, which is C2H6O2. Let me write down that formula. C2H6O2 per kilogram of the solvent. Now, from this figure, we know that from mole, how we can calculate gram. And we have 1 kilogram of water. So let's find the total number of moles rather than using molality. Number of moles from molality, since it's per kilogram and we have 1 kilogram of water. So let's, even though I don't have to multiply, but just to make it simpler, we'll do it. Moles C2H6O2 will be given by 2.69 mole C2H6O2 per kilogram H2O times 1 kilogram H2O. If you had 2 kilograms of H2 instead of 1, you have to multiply by 2. So that's why I'm showing you here the multiplication. So this gives me moles of C2H6O2. Now we know how to go from mole to gram. Mole gram periodic table. So 1 mole C2H6O2. And if we add up the masses of carbon, hydrogen, and oxygen, you're going to get 62.0 gram C2H6O2. And this gives me, so this part gives you moles. I just tried to save some space, and rest of it, if you multiply the whole thing, it would give you gram. So it's going to be 166.78, and you can round it off to, if you want, 167 gram of C2H6O2. So this much of C2H6O2 needs to be added to 1 kilogram of water to get a final freezing point of the solution minus 5 degrees centigrade. Now I'm going to show you how to do problem number 77. In this problem, you're supposed to calculate osmotic pressure. So osmotic pressure is given by pi equals to mRT, where m is the molarity, moles per liter, r is a constant. So let's write down some of these constants. So r equals to 0.0821 liter atmosphere degree Kelvin per mole. So that's our value. T has to be in degree Kelvin, and we know it's in 25 degrees centigrade. So we need to add 273.1 or just 273. So that gives 298 Kelvin. So we need these two numbers. Now in this problem, in 77, they gave you 44.2 milligram of aspirin. So 44.2 milligram, let's change it to gram. That would be 44.2 times 10 to the negative 3 kilogram I'm sorry, that's going to be they gave you milligrams, so it's going to be gram. So 44.2 times 10 to the negative 3 gram of aspirin, and they gave you the formula C9H8O4. And you know how to go from gram to mole by looking at periodic table and adding all the masses. So we can write down, I just added all the masses which should be fairly easy. 180 gram C9 H8O4, and that gives a mole. 1 mole C9 H8O4. So this gives me 2.46 times 10 to the negative 4 mole of C9. Let me write down here, mole of C9H8O4. So we have that many moles. The molarity is going to be will be given by moles per liter, and so let's write down that. And they gave you the volume. So if you read this question carefully, they're saying there's 0.358 liter of water solution. So we're going to make use of that. So let's have number of moles of aspirin on the top. So 2.46 times 10 to the negative 4, that moles of aspirin, divided by the liter, 0.358 liter. 0.358 liter. So that's mole, this is liter. So that gives you moles per liter. And that value is 6.87 times 10 to the negative 4. So molarity is 10 to the 6.87 times 10 to the negative 4. Now I can calculate osmotic pressure by applying that expression. I now know the molarity, which is 6.87 times 10 to the negative 4. So that's molarity value. And the R value, the ideal gas constant, which is pretty well known, which would be 0.0821 liter atmosphere Kelvin mole, and times 298 Kelvin. Okay, now this gives me, after cancellation of those units, keep something in mind. The first quantity has moles on the top, liter on the bottom. So this is mole per liter. And now you can see that mole would cancel, liter would cancel, Kelvin would cancel. So the unit that's remaining will be atmosphere, and that's exactly what we expect here. The osmotic pressure is a pressure unit. So the pressure unit would be atmosphere in this case, 0.0168 atmosphere. If you want to convert it to a smaller unit like millimeter of mercury or torr, you have to multiply that by 760. The 760 millimeter of mercury makes 1 atmosphere.